Okay, notice here I have two graphs, just parts of graphs. One of these graphs is concave up, and one of the graphs is concave down. And I want us to consider what's happening to the first derivative of the graph on each separate case. So if we were going to just consider here, let me do, am I still in red? That red's a good color for this. I want to think about the tangent slopes on this graph. Right here we know it would be 0. These are negative values, and it's hard to get them exactly. And these are positive values. Is the first derivative increasing or decreasing?
Increasing.
It's increasing because we're going from a negative value to 0 to positive values that are getting steeper. So when we are concave up, the first derivative values are increasing. And notice too, when it's concave up, the graph lies above the tangent lines. Okay, just some detail about concavity. If our function is concave up, then that means that the value of the first derivative is increasing. And if you were to put little tangent lines in there, the graph is going to lie above the tangent lines. And I mention that because I've seen a question or two on the AP exam that's asked something in conjunction with how does the graph compare to the placement of the tangent lines.
So it's... the x-axis going to represent as the tangent line?
Pardon?
So the x-axis is going to represent as the tangent line?
That's what those little red lines represent, are the tangent lines that I drew in. Okay, now let's look at when we're concave down. Okay, over here the function f is concave down. If we were to draw little tangent lines, what's happening here? Are they increasing or decreasing?
Decreasing.
Okay, now I didn't hit them right on. I should have, but it's hard to get on there with this end of this pen. So when our function is concave down, then f prime is decreasing. The value of the derivative is getting smaller. And the graph lies below the tangent lines. What do you mean multiple tangent lines? Those are multiple tangent lines.
No, I mean, like, what if it has, like, more than one curve? You have to...
Oh, well, you'd have areas where the graph... You could have areas where the graph is concave up and then areas where the graph is concave down. It could go from one to the other. All right, now, the second derivative test helps us to determine intervals where our graph is concave up and concave down. Is this what I wanted? Okay, this is what we just talked about. Let f be differentiable on an open interval I. The graph is concave up on the interval if f prime is increasing, and concave downward on the interval if f prime is decreasing. Here's an important theorem in this section having to do with the second derivative test. If f is a function whose second derivative exists on the open interval, you have to have a second derivative. Can you think of an instance when you might not have a second derivative?
When the first row is constant?
If your function's a constant. Anything else? Any other time? Well, that doesn't necessarily mean the second derivative doesn't exist. Okay, it might not exist at a point, but it exists somewhere on the interval. What other kind of function would not have a second derivative? If you said a constant function. What about a linear function? Would it have a second derivative? No. So a constant function and a linear function would not have a second derivative. Okay, this theorem tells us that if the derivative exists on the interval, if f double prime, if the second derivative is positive for all x on the interval, then our graph is concave upward. And if our second derivative is less than 0, in other words, if the second derivative is negative for all x in the interval, then the graph is concave downward. Okay. One easy way to remember this is if you think about the graph of f of x equals x squared. Is this graph concave up or concave down? Concave up. We know it looks like this. Except it's centered over here. Sorry, it looks like that. All right, the first derivative is 2x. The second derivative is 2, which is positive, so we know it's concave up. If you have a hard time remembering, if it's positive, I don't remember if it's positive or negative, what that means. Think about that simple basic function. For x squared, our second derivative is positive. Well, we know that x squared is concave up. So anytime we get a positive second derivative, our function is concave up.
What if it's negative x squared?
If it's negative x squared, then it's downward. And your second derivative would be negative 2.